This conference will now be recorded.
Hello everyone. So in this video, we'll discuss previous year's questions of NEET, and that is based on the chapters coordination compounds. The first question we have the type of isomerism exhibited by compounds. So here the compounds are basically mentioned. Here you can see chromium H2O whole 6Cl3, that is the first complex. There will be a bracket. Then the second complex is chromium 5H2O ligands, 1 chlorine, then bracket closed. Outside we have 2 chlorine and 1 water molecule. Look at the third complex, chromium with 4 water molecule, 2 chlorine, basically chloride ligand, and outside the coordination sphere we have 1 chloride and 2 water molecules. So here what is the difference between these three complexes? The difference is whether H2 is present outside the coordination sphere or inside the coordination sphere. Okay. And here the value of coordination number, in short, coordination number is Cn. That also we have to mention. So what type of isomerism is possible for these three complex? Suppose this is complex number 1, this is complex number 2, and this is complex number 3. So the relationship between these three complexes, that is the isomeric relationship that we have to find. And if we consider the coordination number, it is always 6, isn't it? Because H2O total 6 within the third bracket. So the number of ligands within the third bracket, suppose I am writing in general as ML6, or I am writing it as ML5, then another L prime ligand. So in both cases, coordination number is 6, isn't it? So in all these three complexes, in the first one, 6 water molecules directly attached to chromium. That means directly there is coordination bond. And for the second complex, 5 water molecules, 1 chloride. For the last one, 4 water molecules and 2 chloride. But whatever it is, within the third bracket, you always have coordination number 6. So based on that also you can choose the correct option, because only in the last option you have coordination number 6, isn't it? But why it is solvate isomerism, that also we have to understand. So what is solvate isomerism? Solvate isomerism, this is observed in coordination complexes obviously. What is the difference between these isomers? They differ whether or not solvent molecule, mostly you will find the solvent is water. So that is why when the solvent is water, solvate isomers are also known as hydrate isomers. So they differ by whether or not solvent molecule is directly bonded to the metal ion or merely present as free solvent molecule. So in the first complex, all the water molecules directly attached to chromium, directly bonded. But in the second complex, 1 water molecule is outside. So these 5 water molecules directly bonded, but 1 water molecule is not directly bonded. So if I consider the second complex, it will be like this. Total 6 coordination number. So I will write total 5 water molecule here, 2 more, 1 chloride. Now bracket closed, that is within coordination sphere, all we have is this. Outside we have 2 chloride ion and 1 water molecule. So this is free water molecule, so free solvent. So these three are isomers, they are basically related to each other by solvate isomerism. So that is why this will be the correct option. But even if you cannot understand solvate isomerism, then also you can choose the answer, just because Cn is 6, that is mentioned only in the last option. Fine. Homolactic complex. From the following, we have to choose. But here complex structure or formula is not given. What is given is nomenclature. So you have to do two things basically. First, you have to write the formulas. Then only you will be able to understand whether it is homolactic complex or not. But what is homolactic complex? Homolactic complex means where all the ligands are similar type. You will not have two different or more than two different ligands. It will be only one type. But is it really required to draw the structure of all the names as it is given? Because when you will be in exam hall, you will be in a hurry. So without drawing the formulas also, I can suggest that you can understand whether it is homolactic complex or not. How? Though obviously we will see the formulas. but I will try to make you understand how without doing that also you can answer the question whether it is homoleptic or not. Look at the first one. Option 1, it is mentioned diamine. That means here we have NH2, ammonia ligand. Chlorido, that means we have Cl minus. Then nitrito, we have NO2. So three different ligands. How it will be homoleptic? Then the second one, pentamine. Again we have a NH3 carbonato. That means CO3. This ligand is also present. Outside the coordination sphere, we have chloride. Whatever is mentioned after this, that is after the oxidation state of the metal, that is basically outside the coordination sphere. Now the third one, triamine, that means three ammonia, triaqua, that means water is present. Only in the last one, there is only mention of trioxalato. And why potassium? Because this is the cationic part of the complex and this part is the anionic part. Always when we write the nomenclature, the cationic part is mentioned first and then the anionic part is mentioned. How you will remember it? It is simple. Just consider normal inorganic molecule, sodium chloride. How you will write the name? Sodium first, then chloride. So this is the cationic part, this is the anionic part. So same formula is also used here. Now if we actually draw the structure of all these names, what will be the structure? Diamine, chlorido, then nitride, and N platinum. That means here NO2, as it can be attached to metal by through N side or oxygen, so that is why N is mentioned. So diamine means here we will have two ammonia, then we will have Cl, and we will have NO2, and there will be oxidation state 2 plus. Fine. Now the second one will be pentamine cobalt, ammonia 5 carbonato, that is carbonate. Outside there will be chloride. Here two negative oxidation state, and that is two negative charge and one negative charge outside. So total oxidation state is 3, which is clear. Name also it is mentioned. Then the third one, it is chromium complex, 3 ammonia, 3 water, 6 coordination. Sorry, it is 3. Then we have Cl, and here oxidation state is 3. That means if it is 3, to balance it, we need total 3 Cl, isn't it? So it is not that it will be mentioned in the name. You will automatically understand because inside the coordination sphere you do not have any negatively charged ligand. So outside it must be 3 to balance the oxidation state. What about the last one? The last one is potassium. Then the bracket will start. It is basically aluminium complex trioxalato, means like this. Oxidation state is 3. And what will be the total number of potassium? That how we will understand? 3 oxidation state of aluminium and total negative charge you are getting from oxalate is -6. So total 3 potassium must be there to balance the negative charge. Oxalate ligand is like this. So in this way, as you can see, PT, though I have written it, but you can also see in the right hand side, there is total 3 Cl and there is total 3 K. And oxalate, it is also, you can also write it like this, C2O4, because ultimately this structure is C2O4 2 negative. So only in the last one we have single type of ligand, so that is why this should be the correct option. Okay. Next question. The IUPAC name of the complex. Here formula is given. Now as I have mentioned, what positive part is mentioned first, negative part is mentioned later, and when you will actually write the name, then also same thing. So this will be the negative part, this will be the positive part. Now in the positive part we have a third bracket, in the negative part also we have a third bracket, but it doesn't matter how you will name it. When you will actually write the name, you have to focus first on the cationic part. So in the cationic part with silver metal, we have 2 water and water is neutral. So mostly the oxidation state of silver is 1. So suppose there is 1 positive charge. That means outside also 1 positive charge. Now to balance it, we need 1 negative charge. Now separately, if I am writing this anionic part, it will be Ag Cn. Now from each Cn, there will be 1 negative charge. That means total negative charge from 2 Cn is -2. And if it is +1 oxidation state, outside will be one negative charge. So this single negative charge is balanced by the single positive charge of the first coordination sphere species. Now come to the options. The first one is mentioned diaqua silver 2. Now see, just because of this oxidation state, it is not correct. Otherwise, there is nothing wrong in this nomenclature, but oxidation state is not right. Now, what is the problem with option 2? Here, dicyanide, that part is mentioned first. But we cannot write the negative part first. So that is why option 2, option 4 you can easily cancel because it is starting with dicyanide. But that is not the rule. It must be starting with diaqua silver. But oxidation state is wrong in the first option. So that is why third option will be the correct option. And also here one point you have to understand. When it is positive part, silver is mentioned simply as silver. But when it is ending, we are ending the name with the anionic part, it is mentioned as argentate. So just like iron, suppose if when you are writing it in the positive part, it will be iron. When you are writing it in the negative part, it will be ending with ferrate. Okay. So this is the rule. So option 3 is the correct option. Assertion reason type of problem. Assertion statement is saying the metal carbon bond in metal carbonyl complexes, basically metal carbonyls, also sometimes it is mentioned like this, possesses both sigma character as well as pi character. And the second statement is in the reason the ligand to metal bond, there is metal ligand bond. So when ligand to metal bond means ligand is donating to the metal, and metal to ligand bond means when metal is donating to the metal ligand. Now it is mentioned that the ligand to metal bond, that is pi bond nature, and the metal to ligand bond is sigma bond. But is it correct? That we have to understand. Now to answer this question, obviously you should have ideas about the bonding in metal carbonyl complexes. So in metal carbonyl complexes, there is some unique feature. In normal complexes, what you see, it is always ligand is donating negative charge density or lone pair towards the metal. But metal carbonyl complexes, they are so unique that you can have a different type of bonding. So the first type of bonding, as you can see here, it is just like you see in other cases. That is the ligand is donating electron to the metal, and this is basically sigma bonding in nature. The lone pair over carbon that is donated to metal. But this is not the end of the story. The story continues. Once it is done, now the metal where field T2G is there or whatever it is, the metal must have some negative charge density. That is, a metal there should be enough electron density so that this process can occur. Now the metal is donating electron to the vacant pi star orbital of carbonyl. Now when it is happening, this is that is sidewise overlap. It is not head-on overlap, sidewise overlap. So that is, it is pi bonding in nature. So when there is ligand to metal donation, it is basically pi bond, sigma bond in nature. But here it is mentioned that it is pi bond. So it is not correct statement. Only when the metal is donating to the ligand, that is actually pi character. So this is wrong. Correct answer will be if I write like this. So this is not correct. But what is the first one? First statement, metal carbon in carbon compound both possesses both pi. Now this is obviously correct. So here A is correct, but R is not correct. Okay. Ethylene diamine tetraacetate. Ethylene diamine tetraacetate, in short, we write it as EDTA, ethylene diamine tetraacetate, EDTA. Now there are some informations from related to this ligand. Basically, diamine tetraacetate ion is mentioned. Ion is formed from the acid itself. We will see the structure of acid, then you will see the structure of ion, and you will be able to understand how many donor atoms are there and what is the nature of the donor atoms. So obviously we have to write the structure first. So this is the structure of ethylene diamine tetraacetic acid. It is not ion. There is no negative charge. Tetraacetic acid, why? And why it is ethylene diamine? That is derivative of ethylene diamine. Ethylene diamine is this molecule, isn't it? NH2, CH2, CH2, NH2. Now, if you replace these two hydrogens attached to nitrogen with this group, which group? CH2CO2H. Now, CH2CO2H is basically coming from CH3COOH, as if you have replaced one hydrogen with this total group, right? So that is why the name is like this, tetraacetic acid, ethylene diamine tetraacetic acid, because we have total 4 of this part, right? Now if you remove these hydrogens, there will be total 4 O negative. Now when you are doing so, then you can call this as acetate. Now it is in the ion form, and only in the ion form you can have this type of complex. See, this is fully deprotonated iit-jee, all the hydrogens we have removed. Now in presence of metal, there may be many metals that it can complex with, copper, calcium. Now the metal, as you can see, total from 6 side it is bonding with the metal, but among these 6, 2 is from nitrogen and 4 is coming from hydrogen. It is octahedral complex, but there is total 4 donating side from oxygen, 2 donating side from nitrogen, and it is hexadentate. Okay, 2N, 4 oxygen, hexadentate, coordination number. So what option will be correct? Hexadentate ligand with 4O, 2N. That is option B. Okay. Next question, match list 1 with list 2. In list 1, we have some complexes given. In list 2, we have the magnetic moments value. And mostly in the orbital metal complexes, it is mostly the spin only magnetic moment. So how we will understand which one is matching with what? For that, you have to know the number of unpaired electrons. So for the first complex here, the oxidation state of iron is Fe3 plus, because total 6 negative charge is coming from Cn, 3 negative extra. That means it must be Fe3 plus. Now when it is Fe3 plus, it is 3D 5 system. But cyano is strong field ligand. So how we will arrange all the ligands? Sorry, how we will arrange all the electrons? It should be like this. So here we have total how many unpaired electron? We have total 1 unpaired electron. And if it is so, then following this formula, it will be 1 into 3. That means it is basically root 3. Now come to the next one. FeH2 whole 6 3 plus. This is also 3 plus. And here also it is 3D5. But what is the difference? In the previous one, it is SFL, strong field ligand, but now it is weak field ligand. So that is why number of unpaired electron that will be now changed. Now N is equal to 5, and this part it will be 5 into 7, that means 35. Now come to the third one. Now up to this point, if you solve the question, is it possible to choose the answer? That also you should check. Don't just blindly do all the complexes, because sometimes it may happen. Sometimes, I'm not saying always, that just by solving 1 or 2 you can choose the correct option, because the options are so just check it. Here root 35. Now even you don't have to use that is any detailed calculation, because we know root 36 is 6. So when it is root 35, it must be something lesser than 6, which is this one. So A must be matching with 1. Now A, if it is 1, then it is B is matching with 1. Okay, so if B is matching with 1, that means it is present in option 4. But B is 1 that is not present in any of the other options. That means option 4 should be the correct option. So see, just by solving up to the second point, we can choose what is the correct option. And here it is mentioned A is matching with 4. Just check, because A you have already solved. Now root 3, it must be something lesser than root 4, and root 4 is 2. That means it must be some 1.73, which is already there. So A is matching with 4. Now A is 4, B is 1. It is enough to choose the correct option. So just follow this type of, just be try to understand what I'm saying. In this way you can solve, you can save your time. Okay, it is not that always you have to solve everything. Now we will also do the rest of the 2. C is matching with 2. Now C is Fe2. Fe2 is 3d6, but it is strong field ligand. So as it is strong field ligand, there will be no unpaired electron. It will be that is T2G6. That means N is equal to 0. So C must be 2. If C is matching with 2, only one is left, which is this one. Now this is 2 plus, and 2 plus means it is again 3d6 with weak field ligand. And in weak field ligand, if you arrange it, you will see you will get total. So here n value is 4. That means it is root 24, which is near about 4.9. So option 4 will be the correct option. Okay. The type of isomerism shown by the complex cobalt 2 chlorine 2 En2. Now En is this one, and this is symmetrical bidentate ligand. That means you can express it like this. So this complex, general way if I write it, it is MAA whole 2 and B2, B is Cl. Now for this type of complex B2, what are the possibilities for that is whatever isomerism we can expect? So ionization isomerism. Now ionization isomerism, that means after ionization we will have different anion and cation, but that is not possible here. We have only one type of anionic ligand. Then coordination isomerism, that is also not possible. Geometrical isomerism, yes, it is possible. Basically, see, when you will be able to understand the type of the complex, that is the general type, as I have written the formula, just by looking at the options you will be able to understand, even you don't need to go to the details. Geometrical means cis-trans isomerism. Now cis-trans isomerism, it is possible because this is where these two B, they are trans to each other, it is 180-degree. But another structure also you can draw where these two B, the relative arrangement, it will be cis 90-degree, and rest of the part I am writing AA so that general way you can understand. So all these are, that is here, these two B, they are cis. So cis trans isomerism possible, that means it will show geometrical isomerism. Linkage isomerism also not possible, because in linkage isomerism is observed, suppose we have NO2 as ligand, and NO2 ligand, if it is binding through oxygen side, that is one possibility. If it is binding to nitrogen, that is another possibility. But that possibility is not here, because linkage isomerism is possible only with some specific ligands where two donating sites are there, but these type of ligands are not given. So that is also not correct option. Geometrical isomerism is the correct option. Geometry and magnetic behavior of the complex NiCO4, that means tetracarbon. So here we have option 1 is saying it is square planar, 3 is also saying it is square planar, only difference is dia-para. Option 2 is saying it is tetrahedral, 4 is also saying it is tetrahedral, only difference is dia and para. Now square planar tetrahedral, in both cases coordination number is 4. So how you will understand it? To understand it, you have to look at the electronic configuration of nickel. Here nickel is attached with neutral ligands. That means oxidation state of nickel is 0, because overall there is no negative or positive charge. Now if oxidation state of nickel is 0, that means nickel is 0, it is having configuration 3D8 4s2. Now when it will form complex, what will happen? These two ligands, it will come here, and ultimately it will be 3D10, because CO is after all strong field ligand. It has the capacity to pair up the electrons. Now if it is so, now see what is the difference. In the first case, it is 3D8 4s2. This is basically 4p. Now these two electrons are coming here. All the electrons are paired up. Now you are left with S and P. So here sp3 hybridization possible. Now sp3 hybridization means it will be tetrahedral. If it is dsp2, then only there is a possibility of square planar complex, but that is not the case. So it is tetrahedral, it is sp3, though hybridization is not asked here, but still for extra information, because same type of complex you can also get another type of problem where it is mentioned that find the hybridization. So it is always better to have some extra information. And here, how to choose whether it is dia or para? You can see n value is 0, there is no unpaired electron. So obviously it will be diamagnetic. Now here I would also like to say a few more information. Suppose this complex is given instead of nickel CO4. Now what you will do? In this case, the oxidation state of nickel is basically +2 because we have total 4 cyanoligand, outside charge is 2 minus. That means nickel must be 2 plus charge. Now when it is 2 plus, nickel is 3d8 already because 4s is 0. Now when it is 3d8, it is nickel atom, that is it is 3d8, this is 4s2. But suppose these two electrons are now lost, you are left with this configuration. Now this electron will come here and there will be pairing. So up to this point there is pairing. This d is vacant. Now this is dsp2, this hybridization, that means in this case it will be square planar. So I am giving extra information because sometimes you can get question that nickel CO4 is tetrahedral, but nickel tetracyano, that is this cyano complex, that is square planar. So that is comparison related question also you may get. Fine. An example of sigma bonded organometallic compound. Organometallic compound means what? Organometallic compound means where metal carbon bond will be present. That is why it is organometallic. Organo term is coming from carbon and this metallic term is coming from N. So where metal carbon bond is present, we call those compounds organometallic compounds, and the specific characteristic is that carbon is more electronegative than metal. So whenever you will consider the polarity of this bond, then positive charge, I am writing del plus because the bond I have not fully broken it, and this is del negative. If you are breaking it completely, it will be M plus and C minus. So negative charge, it will always be towards carbon. Now the four options given: ruthenosin, Grignard reagents, ferrocin, cobaltocin. In which case the organometallic compound is sigma bonded. That means the bond between metal and carbon, that is sigma bond character, not pi bond. But sometimes there may be pi bond also. In this case, the bond that I have written, that is basically sigma bond. But suppose you have cyclopentadiene like this. Here we have two hydrogen. Now if one hydrogen is removed, then what will happen? There will be negative charge. Now in this case, this negative charge is completely delocalized like this. Negative charge can be shifted to the next carbon. Now that is why sometimes it is also written with this type of circle. Now this pi bond, if it is donated to metal, then you will have not sigma bonded organometallic compound but pi bonded, because the pi electron cloud is donated, not sigma electron is donated. Okay, that is the difference between sigma bonded and pi bonded organometallic compound. Now when it is Grignard reagent, general way I can write Grignard reagent as R. R means any alkyl group, then MgBr. Now this R may be methyl, the simplest example I can give you. So CH3 MgBr. So here Mg is bonded to Br, Mg is bonded to methyl group. Now Mg is obviously more electropositive. Suppose if you are breaking this bond, Mg will have 2 plus charge. And if you are breaking this bond, basically you will get methyl negative. So this is an example where it is sigma bonded organometallic compound. But what about the other three? The other three molecules are like this: ruthenosin, ferrocin, cobaltocin. So here I have already shown this type of pi, that is 5-membered with the two pi bond and one negative charge, but because of resonance I have written it like this. Now this both side, another side, suppose another side also the same thing is possible. Now whether this metal is ruthenium, iron or cobalt, based on that you can have different names. And obviously here the charge over this metal is always 2 plus charge. Fine, because see, this is one negative charge coming from one 5-membered ring, another negative charge is coming from this. So carbon metal must have two positive charge. So these are the structures of ruthenocene, ferrocene, cobaltocene, but all are obviously organometallic compound, but they are not sigma bond. They are pi bond. And if you actually want to see their how they in 3 dimension how it will be, then you should draw the structure like this, as if iron is sandwiched between two 5-membered ring. Okay, so correct option is Grignard reagent. In a similar way, just read the question carefully. Suppose in it is asked in a different way. An example of pi bonded organometallic compound. Then our correct answer will be ACD. Okay. Though single choice answers are always there, but I will suggest always to read the question carefully, because in that case maybe 3 options are given where all of them are sigma bonded. Only one ruthenocene or ferrocene is mentioned. Okay. So these are the different ways, but concept is same. Different ways the question may be designed. The correct order of stoichiometries of silver chloride formed when silver nitrate in excess. It is not that some mole numbers are given. In excess is mixed, is treated with these complexes. How many complexes we have? This is the first complex. This is the second complex. This is the third complex. Now the formulas are given in such a way, it is not given within third bracket, so that you can understand what are the species present inside the coordination sphere, what are the ligand species outside. That you have to draw yourself. Okay, so the formulas are given like this. So correct order of stoichiometries of AgCl form. Now what it means actually? The formula, that is when we write like this, ML6 or L5, whatever it is, the ligands that are present outside. Suppose when Cl is present outside, then only it can react with Ag plus, which is coming from AgNO3, and it can form AgCl. Suppose if the Cl is present inside, suppose outside there is nothing. If Cl is present inside, then it cannot react with Ag plus because it is not free. It is directly bonded to metal. Only the chloride outside coordination sphere can react with Ag. So basically it is asking how many chlorine is present outside the coordination sphere, and look at the options. That is 3 AgCl. That means, suppose option A is correct, 3 AgCl, that means from first complex all the chlorine they are present outside the coordination sphere. 1 AgCl, that means 1 Cl is present outside this. So this is the meaning of this question. Now remember, here with cobalt we have two different types of ligand, Cl minus and we have ammonia. Now Cl minus is negative ligand, but ammonia is neutral. Now neutral ligand is not present outside the coordination sphere. In some hydride complex you can see H2 outside, but ammonia it is always inside. Now if that is the case, then the formula of the first complex should be all the 6 ammonia inside. Now if all the 6 ammonia inside, that means coordination number is already fulfilled. 3 chlorine must be outside. Similarly, for the second complex, 5 ammonia must be inside. That means 5 coordination fulfilled. You need 1 more Cl. If it is so, only 2 chlorine, 2 Cl minus will be left in the outside. So in this way, you have to understand the formula. So this should be the formula. In the first case, all the ammonia inside. Second case, only 5 ammonia. So 1 Cl you need inside. In the third case, you have total 4 ammonia, but you need 2 more. So outside only 1 Cl. So you will get 3 AgCl from the first, 2 AgCl from the second, and 1 AgCl from the last. That means option B should be the correct option. So this is the actual reaction. As you can see, here 3 AgCl is you are getting, and that place is taken by NO3, which is coming from silver nitrate. Here 2 NO3. This Cl is undisturbed. It is still there. This chloride is undisturbed. It is still there. 1 NO3 is here. So 3, 2, and 1. Option B correct. Pick out the correct statement with respect to this complex. Here we have two hybridization mentioned, sp3d2 in option A and D, and Second type of hybridization, D2sp3, option B, DsP2, option C. Now here it is hexa coordinated. Coordination number is 6. Sorry, the coordination number is also C, and don't be confused. C dot H N dot means coordination number. This is 6 because 6 iron ligands are there. So it cannot be correct. Now whether it is using 3D orbital, in that case it is D2sp3 inner orbital complex. If it is using 4D, then it is outer orbital complex. It will be D. So what we have to do, how we will start? Mn oxidation state you have to write first. Oxidation state is 3+. Now Mn, when it is neutral, it has configuration after argon 3D 5 4s2. But in this case we have 3D, it is Mn3+, that means it will be 3D4. But how we will write all the electrons? Remember here we have the nature of the ligand, it is strong field ligand. So when you will actually write it, it will be 1, 2, 3. Sorry, it will be not here. You can also write directly in d orbital. Now 1, 2, 3, but there will be a pairing, as you can see here. So 2 electrons are still unpaired, but we have now vacant 2d. So it will be D2sp3 hybridization. Now if it is so, D2sp3 hybridization, so we are left only with option B. And obviously it is octahedral, it cannot be tetrahedral. Now see, okay, this is also octahedral. So based on octahedral, you cannot choose correct option, because if you are this, you can easily cancel. This also you can easily cancel. But now you are stuck between B and D, and now you have to understand whether it is D2sp3 or sp3d2. Otherwise, both are same. So on the basis of octahedral, you cannot choose, right? So it is octahedral, D2sp3, option B. Jantler effect is not observed in high spin complexes of D7, D8, D4, D9. Now what is Jantler effect? Jantler effect is basically observed only in some specific cases. There are some specific electronic configuration where you will have this effect. But what is this effect? This effect is actually geometrical distortion. So geometrical distortion means the original structure, there is this distortion, and the complex try to remove its symmetry. That is why it is distorted. Distortion of molecules or ions depending on whether the complex is neutral or a negative charge or positive charge because of certain electronic configuration. So only in some specific cases you can have this effect. But what are those specific cases? It is observed in those octahedral complexes where d electrons are filled unsymmetrically. That means degeneracy is possible. Now degeneracy possible means, look at this. Here all of them are basically high spin, Hs. Low spin also you can draw. So D1 in T2G and EG, D2, then D3, D4, D5. Now you can see two different color. If you focus on the red ones, you will see here degeneracy is not possible, because even if you change the position of electrons, suppose you are exchanging these two electrons, you will not have new configuration. But look at the black ones. If you are placing this electron here, you will have different configuration. That means in the black configurations, you can have some degeneracy. You can have same energy level but different configuration. But degeneracy not possible in the red ones. So in the red ones, where it is symmetrically filled, Jantler is not possible. Jantler is possible only in the black ones because they are unsymmetrically filled. Now just for example, see this unsymmetrically filled, it can be two types. Is the unsymmetry is in T2G or EG? So see here, just focus on these D6. Here unsymmetry is in T2G. Now look at D4. Here unsymmetry is in EG. Now both unsymmetry is possible. Remember, in both cases Jantler is possible, but when it is in EG, it is more intense. Though that information is not required to solve this question, but I am just saying this for extra information. So Jantler effect will not be observed in which case? When it is D7, See, in D7 there is unsymmetrical arrangement in T2G, so it is possible here. In D8 it is already, you can see it is red and it is symmetrical, so here it is not possible. This should be the correct answer. In D4 there is unsymmetry in EG. In D9 there is unsymmetry again in EG. So D4, D9 there will be strong Jan-Taylor. I am not saying D7 there will not be Jan-Taylor, but it will be comparatively weak. Why I am saying so? Because sometimes you may get question where it is asked in which case Jan-Taylor effect is very intense. So that you can compare. So that is why I am just giving this extra information. When there is unevenly occupied T2G, Jan-Taylor is weak, but if it is unevenly occupied TG, Jan-Taylor is strong. But in our case, we just have to find in which case it is not observed, and the correct option is D8. Okay, option B. Which of the following has the longest carbon-oxygen bond length? Now, this is metal carbonyl complexes, obviously, from the options that you can see. Here, free CO bond length is also mentioned. Though that value is not required, it is just extra information. But in which case there will be maximum bond length of carbon oxygen. It is basically related to back bonding. Now this picture you have already seen in one problem I have shown you. So here we know where sigma bonding is there. It is electrons are coming from ligand to metal. But when it is pi back bonding, electron density is going to metal to ligand. Now when this pi bonding is occurring, what will happen? The metal carbon bond length will decrease and carbon oxygen bond length will increase when there is back bonding increasing. So what I'm trying to say, when back bonding is increasing, suppose in one metal complex back bonding is not so high, another metal complex back bonding is high. So when back bonding is increasing, metal carbon bond length will decrease and carbon oxygen bond length will increase. Why? Because when this is happening intensely, this triple bond nature between carbon oxygen that will be removed. Now there will be some double bond character. So bond order is basically decreasing for CO bond. Now bond order, how it is related to bond length? Inversely related. So when bond order is decreasing, bond order decreasing means bond length will increase. So this triple bond nature, now it will change to double bond nature. So that means when back bonding is very high, carbon oxygen bond length is also longer compared to the situation where it is not so high. Now look at the options. Here nickel is 0 because carbonyl, they are neutral. Negative charge, that means here oxidation state is -1, oxidation state is -2, here oxidation state is +1. Now comparing the oxidation state, in which case the most negative charge density is present, it is obviously the iron because we have two negative charge. So when negative charge density over the metal is very high, that means the chance of back bonding will be very high, isn't it? So when back bonding is maximum, CO bond length is also maximum and we have to find that longest CO bond, isn't it? So this should be option C, iron carbonyl complex with two negative charge. That should be the correct option. Okay. But for extra information, I would also like to mention, suppose the question is asked in the order form. So in 4 options, different orders are there. So here CO bond length is maximum. After that, it will be this cobalt complex because here it is -2 charge, here it is -1. Then in case of this nickel, it is 0 and only in this one it is +1. So gradually the negative charge is going towards 0, then positive. So that means CO bond length will gradually diminish. So this is the order for CO bond length, but we just have to find this one, that is the maximum, in which case this bond length is maximum, we just have to find them. And that is why this should be the correct option. That is option C. We just have very few minutes, we'll solve this problem. Now see, in previously this NEET is known as AIP-MT, so that is why as we are going backward, it is the name of the exam is changed. Okay, the name of the complex ion, that is FeCN6 3-, that we have to find. Now as you can see, it is anion, so obviously it will end with ion. but that is present in all of them. Next, you can see what is the oxidation state. It is +3. That means this cannot be correct. Now, it is hexacyanidopyrrate. Now, option it is mentioned cyanido, which is not correct. Now, CN is not written as cyano. Okay, sometimes in organic compounds it will written so, but it is not cyano. It is basically, sorry, it is, even if you do not consider it, it is tri. So how it can be correct? So that these two you can easily cancel. That is option B, option D you can easily cancel. But it is not cyanido. Spelling is not correct. It is cyanido. Otherwise, option A, only because of this T it is not correct. It is cyanido, and it will end with ferrate, because after all it is the negative, it is carrying some charge. It is the anion, so it is ending with ferrate, then oxidation state and ion. So option C is the correct option. Fine. So we have solved. We cannot. We are at the end of the session. We cannot solve more. Okay. Thank you for listening.